Okay, so it's time. So let's start. So we have more students than before today. So from now on, we are going to talk about the integration. And last week we had a midterm. So to wrap up before we move on to the new topic, let's review some questions that I asked in the midterm. So I posed 4 questions in midterm. Okay. So these are the questions. So first question asks, what is the derivative of a function? And second question is, what is the chain rule? Why is the chain rule important? And third and fourth question is about how we find the maximum minimum in certain condition. So basically, I asked 3 categories. So one is what, and other is why and how. And these 3 categories of questions are the main form of question that you can ask and answer in any scientific research area, or any part of life. If you really want to think something, you have to think about 3 things: what, why, and how. So what is the derivative of a function? It's a simple question. You have to define things. So particularly in mathematics, when you're asked to explain what is something, then you have to answer in a concrete way, not that you have to explain the meaning or the consequence, just to describe the what is that object. So I'm asking about a function, and we talked about the function is either single variable or multivariable. And in general, function can be non-continuous or continuous, but when you're talking about the derivative, then obviously we are talking about continuous function that you can measure the value of function by changing the value of inputs. And the concepts of derivative is integrate with the differentiability of a function. So when you talk about the derivative of a function, you have to say that it is a function that has the value of the differential. And when you want to measure the differential of a function, you have to talk about the differentiability. Okay, so these all kind of concepts appears by one question: what is the derivative of a function? So I'm not going to give another answer, because the answer is, there's no one answer. So there are plenty of ways you can answer this question. So and also we covered it in the class, so if you're really curious, you can go back to our lecture, or the best way is just look at the textbook. And second question is, why is the chain rule important? And that's actually the key question that I wanted to ask, because so I'm not asking the universal reason why you have to think the chain rule is important. It's all personal. So the important is very personal word that each of us has own reason why we think the chain rule is important. So I gave one reason in the lecture. For example, we used the chain rule to think about the differential of a function in certain direction. We used the chain rule. And also we talked about the Laplacian. When you express the spherical form of Laplacian, we need a chain rule. And that's the application of the chain rule, and you can consider that is the why the chain rule is important. Or you can have a different reason, because I saw many, or almost all of answer to this question was because chain rule is because the chain rule says the derivative of composite of two functions is the multiple of derivative of each function, so it makes its computation easy. And that's the period. And that follows the immediate question that why does it make it easy? Why does it taking separate derivative of two functions and multiply together makes it easier than taking a derivative of composite function? Because if you take the composite of two functions, maybe each of two functions are very complicated, and somehow if you make a composition of these two complicated functions, then the result could be a lot simpler function. And taking a derivative of that simple function could be easier than taking a derivative of two very complicated functions, right? So you have to explain why make it easier, right? And I know why you say it's easy, because I somehow maybe in the lecture, maybe this kind of strategy is easier in general, but I didn't provide some examples, so part of it is my fault, but you have to have your own reason why you think that is easier than not using the chain rule. So anyway, my impression when I read your answers to this second question is that, by the way, so there was one student who answered this second question in a very personal way, and I really liked that, because he said that this question is wrong, because you have to say, before you say it's important, you have to say for what purpose this chain rule is important. And he was laying out why, in his own personal view, why it's important in his future career and also his research interest, and so on. And so, but most of students answer this question something like, I made this presupposition that the chain rule is important, explain. And you're forced to explain why it is important. But my real answer, my real motivation was that just explain why you feel that it is important, or why you thought that it's important. Not that I imposed that the chain rule is important, but provide your own thinking or your own reason why you think the chain rule is really important. So if you haven't thought about the chain rule much, then you probably couldn't answer, but just repeating what I've just said in the lecture or my thinking. So that's that. And third one, how is the gradient used in the finding maximum minimum point on the contour boundary? So that's actually a hard question. It's asking about the, technically it's a Lagrangian multiplier. And there are a few students who answered that correctly, but my intention was not to, you don't have to explain in a general sense of this question. So when we ask how, then there are several ways you can answer these questions. You can answer in a most general way that you can apply any type of functions or any type of object to this strategy, or you can just show concrete example that fits into this category of questions. And this is how, for example, you apply or you explain this kind of situation. So, for example, we talked about the gradient method, gradient descent, and during the gradient descent, we explained why the gradient direction is the direction that changes the value of function in a steepest way, or in other words, the fastest or slowest way. So during that time, we talked about the direction is determined by the point on the unit circle, and among the points on the unit circle, it's a matter of finding the point where the vector that points to that point on the unit circle is the direction that changes the value of function the fastest or slowest rate. And we discussed that happens when the contour boundary of the circle, in this case, it's replaced by g equals to c, is tangent to the contour boundary, or the level set of the function f. So you can explain that. I mean, some students actually try to explain that in a nice way. But you have to answer the fourth question. If you have read these two questions in the same time, then they're asking this two different situations. So first one is finding maximum minimum on the boundary, and for the last one is finding minimum and maximum in a general domain space or domain plane. So most people referred the theorem that called maximum minimum theorem, and that says that there is a minimum maximum if you take the closed boundary, closed set, or closed domain of your function as the domain of function, then you always have a minimum or maximum in that closed set. That's true. That theorem is true, but that doesn't tell you where you find that maximum or minimum. It just tells you there exists a minimum and a maximum in that closed set of domain. So the question is, how do we find the specific points of the function? And that's actually the way we describe determining the minimum or maximum, or could be saddle saddle properties of the critical point. So you first find the critical point and determine whether it's maximum or local minimum, and saddle by taking the determinant of Hessian, and then so on. And I was hoping that you could go further than that, because once you find that local maximum or minimum, if the domain has a boundary, then you have to compare the maximum and minimum on that boundary with the local maximum minimum you found inside of the boundary, so that you can find the global maximum or global minimum in the domain. So you have to go back to the third question to find out where is the maximum and minimum along the boundary. And most people fail to say that because most students say that first find the local minimum maximum using the Hessian, and then compare that value with the values on the boundary. But if you think about the value of the boundary, if it's a multivariable function, then the domain is at least two-dimensional domain. So your boundary consists of infinitely many points. So this is the boundary in two-dimensional plane, in two-variable function. So you cannot find the value of function in the boundary unless you can find infinitely many numbers, right? So in a single variable case, boundary is just two points. So it's simple. But in a two-dimensional or two-variable function, you cannot simply just say you can compare the value on the boundary with the local maximum or local minimum, saying that they are here. You cannot compare that. So you have to find along this boundary where you take the maximum or where you take the minimum, and you can compare these finite values, and the largest one is the global maximum and smallest one is the global minimum. And that's my intention, but I try to give I try to give a good feedback on any type of answer that you gave, even though it's not a perfect answer, because there's no perfect answer in my point of view. As long as you are logical and sensible, then I think any answer is correct. So besides the content of the answer, I wanted to mention about the writing itself. So whenever I write something, I try to make it as a full sentence. Although in the lecture, I fail to put every sentence in the full sentence because it's simply because of a lack of time and space. But if you have plenty of time and you're asked to write something to be read to someone else, then you have to write everything in a full sentence in a correct grammar or correct way of writing, and that's basically mathematical writing, and you have to use the formula in a proper way, and you have to use the proper symbols. But we are accustomed to, from very early time when you start learning mathematics in a elementary school or middle school, I think it's bad customs to teacher to write everything in symbols and numbers and not writing any words when you explain mathematical things. But as I said again, mathematics is a language. It's a language. Okay, language is it's a rule between people. Okay, so you have a certain rule to deliver the proper content through the language, right? So mathematics is not just an idea or not just the computation. It's a language, so you have to obey the rule that mathematicians or any people who use the mathematics in their research area sets that this is our rule. So I think it's a part of my job to show you the proper use of the mathematical language. So I try to, I will try to show that more in the second half of our class. So if you have any questions, please ask now about these questions and midterms and anything else. So before we really start the second half of our lecture, so I really want you to read the textbook because, you see, these 4 questions, it's a summary of what we have learned so far, and that's a summary to the first half of our textbook. So first half of our textbook tells about the derivative of a function, specifically multivariable function. And you start from the what is derivative, and now the concepts of partial derivative and directional derivative follows. And then really important thing is about the chain rule. And there should be an application to the derivative or chain rule, and that's the finding minimum and maxima of a function. So I tried to explain that concept through some mini project that I showed you in the lecture. And I really want to do that similar thing in the second half of the lecture to explain the integration. So I've thought about it quite a while. And I think I haven't found that good mini project to incorporate the idea of integration. So far, my plan is to deliver the idea or mathematical concepts of integration in the motivation of physics. So there are many physical concepts like flux or line integrals to find the work done from here to there and so on, to motivate why we should learn the integration. And if you are a physics major, that could be enough motivation to learn the integration. But if you are like biology major or so on, and maybe it's kind of not a good motivation or not very interesting. But anyway, that's how I could, as far as I could find the best motivation for the integration. And it would be good if you find your own motivation to learn the integration part as well. Okay, so let's talk about the integration. So besides any motivation to learn any mathematical concepts, the differentiation and integration is very interesting concept. So we know what differentiation is. We take the difference between function and the input and take the kind of somehow ratio between these two difference and then find the limit, right? And we probably learned that integration is kind of a reverse process of differentiation, right? There are words something like antiderivative. So it's in a Korean it's called 역도함수. So 도함수 is derivative and 역도함수 is antiderivative. So you say it's integration is somehow opposite of derivative or derivation. So you can question that. Is it really an opposite? Then you can ask, if you assume that this is the opposite, integration is opposite to derivative, it makes sense to single variable function. Then what does it mean when you take the multivariable function to say that integration is opposite to derivative? Like derivation is finding derivative, and derivative is the function that takes the value takes the point on the domain space and then gives the differential in a form of matrix. And what does it mean that you reverse that process to integrate? It somehow doesn't make good sense to me. I mean, integration for me doesn't make the good sense. So it's not, I mean, personally, I think the high school curriculum, especially in mathematics, doing a bad job to explain the true meaning of integration and derivatives. And they are really technical, and they're delivering, I mean, they're doing good job delivering the technical process of derivative and integration. But if you are in the person from 60s or 70s, that could be a really important issue because there are no computer power. You have to do your integration and derivative by hand. But now you have a calculator, and not just a calculator that does the integration and derivative and all sorts of complicated computation for you. Okay, so you don't have to do the computation by yourself. And many type of functions cannot take a derivative by hand or cannot take the integration by hand. So you have to use the computer. And what's use of doing all this computation by hand if you cannot use your hand? in real situation. So let's talk about the integration first. So let's talk about the integration of single variable function. So before we begin, I want to pose a question. What is a integration? So this is a very vague question in a sense that the integration is a noun form of verb integrate, and integrate needs a subject and object. And subject is always me or you or we, so it's a human that integrates, right? And it needs an object. What do we integrate, right? So in the word integrate, in the English word in integrate, it's like a gathering something, right? You have to provide what are you integrating. So the correct question should be what is the integration of a function, right? So whenever we take a notion of a function, then you have to separate it into two categories. One is single variable function, and the other is multivariable function. And the way I provide you about the idea about multivariable function is starting with the set concepts in the single variable function. Just because you're familiar with the thing that with the single variable function. So let's think about the single variable function case. So what is the integration in a single variable function? So for example, let's say I have y equals f of x, and our domain is closed interval from a to b. How would you explain the integration of this function on this domain a to b? Kono? Juno, sorry.
I think integration of single variable function from A to B is like process to find out the surface of F, where the domain is defined in A to B. Or if there's no defined 정역, there's no defined 정역, it is like process to find out a vague shape of function. Yeah, I think there is.
Okay. So Juno answered in the two directions. So if you provide the interval of integration, then it's finding a surface of a function. If I made it correctly, then, and if you don't provide with the interval, then it's like finding a vague geometric shape of a function. In a sense, I know what you mean. If you're provided with the context of what you have learned about the integration, you probably agree that's true, and that you probably agree with what you said is same as what the context is. But I think we have to be more specific about what you mean by integration is getting a surface of a function. So, for example, surface is a surface. It's not a number. So I'm asking, the integration gives you number or some geometric shape?
I think it is more like geometric shape.
Geometric shape. Okay.
Surface, positive number, I think.
Okay, so that's good. Anyway, so let's talk about the symbols that we have already known from high school. If I want to be more specific, then is it a number or a shape? It's a number. And what do we call this?
I don't know how to say in English, but I say it is
You say what? Okay. So we call this an integration. So it's in Korean it's 적분, but more specifically it's in English it's called definite integral. In Korean it's what is it? 정적분. Okay. And June also said that there is an integration without this a to b, right? So we're going to talk about this later, okay? And this is called the indefinite integral. And it's a side talk, but this time is the period that the students, high school students, are applying to our university, and they are asked to answer some mathematical questions or science questions to check their understanding on their the content, the high school content. And I look up their textbook, and how they explain this definite integral is to define the indefinite integral first, and then try to make this is equals to the difference of the indefinite integral from a to b, and so on. So it's basically they're using the fundamental theorem of calculus as a definition of definite integral, and that's wrong. It's really wrong. It's not a definition. It's just theorem. How we should start with a definite. How we should start the integral is from definite integral. So I know your idea about geometric surface thing to explain the integral, but this is a number, this is a value, and what does this value represent geometrically?
It is height difference
Uh-huh.
in a definitive function, integrated function.
This is called the integrand. For yes, this function inside the integration is called integrand. That's actually good to write a definition here. So this whole thing is called definite integral, and this function inside the definite integral is called integrand. In Korean, I think it's 피적분 함수. So this is actually out of Korea. It's a Chinese. It's derived from the Chinese letter, right? And most of mathematical words based on Chinese character came from the Japanese word. Okay, so that's why it's kind of weird. It feels weird, right? So somehow using English word, it's more. I think it's intuitive in some sense. But anyway, so what was your, what did you say? So this represents height between, difference between,
in indefinite integral function.
height difference between indefinite integral. But let's forget about indefinite integral for now. So we have a function, and we are doing something in this interval from a to b. Right? And you got this number, and what does this number represent in terms of this interval and function? Anyone else?
The area surrounded by x-axis and
Uh-huh.
x equals a,
Uh-huh.
x equals b,
Uh-huh.
fx.
Right. So area surrounded by graph of function and the x-axis. Right. So and also you have to put a boundary on a to b. So I think what June tried to say is similar, or you have learned that thing before. So this is the area So I want to put a quote on an area because this area is a negative if your graph of function is below the x-axis. So you're not taking the absolute area, but the area with a sign. So putting a quote here, graph of a function and x-axis in A to B. So if you draw that situation, this is our picture. So this is A to B, and y equals f of x, and this area is the integration, right? Everyone knows that, right? I assume that everyone at least seen this picture before, right? So we're not going to talk about indefinite integral yet, okay? Let's talk about multivariable function. You can look up the definition in the textbook, but I'm trying to give you an idea how we can generalize this concept of integration from single variable function to multivariable function. So we have a multivariable function, for example, z equals to f of xy, and we need a domain. For example, let's take a square domain or rectangular domain. So my xy lies in A to B cross C to D. So this is A to B is the range of x, and C to D is the range of y. So we have rectangular region here. So I want to say similar thing. Let's say, for example, instead of writing this whole thing, I'm going to replace that with D. So D is the rectangular, D means the rectangular domain. And I want to integrate this function. Now it's a two variable function. As we put the x inside of the integrand, we can put xy's in the integrand. And with the symbol dx, we know that this is somehow the way we write the integration. So we can put dx dy if you want to, just as a symbol to represent the integration. And what would this represent? Since this is a number, this should be also number. But I want to generalize the idea of integration, geometric idea of integration, to the idea of integration of two variable function. What should be the native or natural generalization? So we had a U face here. So Jaemin, do you have any idea? So what is this is just a guess. What do you guess the meaning of this value in terms of a function, two variable function, and the domain D? In the sense of generalization of the integration of single variable function. So it's a very good strategy if you are stuck with any question, then it's good to have a conversation between friends. So we have friends who can get together. So maybe I think all these three students are friends each other. I think you can discuss with 3 persons there. I know there's someone who I know the answer, right? So discuss and find if anyone knows the answer, and then I will ask you to explain the answer or say the answer that came from other people, other students, okay? Not your answer, but the other student's answer, okay? Just discuss these 3 students here. I know that you know the answer at least, right? So you can explain the answer to other students, and other students can explain how other students can answer that question, okay? you can discuss with these three. So anyone from Zoom can also think about the question, or you can look up any context in the website or in the textbook. So the keyword that you can search for is double integral or multiple integral. And then see how any textbook or mathematical page explains that concept. All right. So what's your name? Yongseok. Okay, so sorry, we met twice. So do you have an answer from, did you have an answer from other students? Yes, the volume of what? Right, so simple answer, right? So it's the volume, but I'm going to quote this also because if you have a graph underneath the x and y plane, then that volume should be a negative volume, similar to the negative area in the single variable case. So the volume between the graph z equals to graph of, so you have to be really careful about the writing. So volume of the function on the two-dimensional plane D and xy plane. So if you draw this geometric situation in 3D dimension picture, then you have x and y and z, and you have graph of function here, and we have a square domain. So basically you have a to b, and here we have c to d, and this is our d inside of xy plane. We are measuring the volume between this xy plane and the surface of graph of function, and surrounded by this boundary a to b and c to d. That's the idea. That's the integration. And that is the integration. I mean, there's nothing else, right? So instead of taking one s here, so you know that this comes from s. The integration sign comes from s. It's s from sum. Okay? And instead of one s, we have two s, meaning that we are taking in this the geometric object between the two-dimensional surface. One is this graph of function, and the other is the planar surface. Okay? By the way, if you have a three-variable function instead of two-variable function, how many s you need? Is 3. You have to put more s according to the number of inputs here. Okay? But if you see more advanced literature in physics or mathematics deal with this integration, they don't use this double S or triple S. Instead of, they just use the one S, because integration is nothing about the number of S here, just idea is important. So anyway, we defined that thing, and defining the thing means that you can actually carry out the computation when you are given with an example, right? So for example, if you have a two-variable function as a linear function, like say you have a linear combination of x and y as a formula for fxy, then your graph is like plane or tilted plane. Then you can find the volume by just taking any idea from the geometry, right? You just take the area of a volume of a triangle or like rectangular volume or something like that. But if you have this round surface, then what do you have to do in order to find the exact volume between this round surface and the surface xy? What did we do in defining the area between the graph of function and x-axis? Right, so you divided your area into very thin or very small rectangles, meaning that you're chopping off your domain. You're chopping off the interval from A to B into very small pieces, and you're taking a rectangle on a small pieces, and then you add up those pieces, and then hoping that the adds will converge to number when you increase the number of choppings. Right? You do the same thing in here. You're chopping off this domain. Right? So if you have x and y and A to B and C to D, you divide your x-axis and y-axis into many, many pieces, although I can draw only a few in here. So let's say I have drawn in n pieces, and here we have m pieces, and I want to let n goes to infinity after all, and m goes to infinity, and then try to see that the volume underneath each of this small area and is given by the volume of rectangle. And if you add up all this volume of small rectangles, and when I take the n and m goes to infinity, and somehow I'm hoping that this sum goes to some fixed limit. So when you take the value of, the volume of rectangles, you need a height, right? How do you take the height? Which x and y coordinates? So for example, if I take the volume of a rectangle on this small rectangle, how would you take x and y coordinate to compute the height? Mm-hmm. Any points? Right. You can choose midpoint or the point on the boundary. You can choose any point, right? That's how you choose a point in the Riemann sum of the definite integral, right? Basically, you can choose a left point or right point, or take a midpoint, but basically you can choose any point. So here's the same. You can choose any point. Let's say xi and yj. So I runs from 0 to n, and j runs from c to d, 0 to m here. So basically, I'm supposing that this sub intervals are evenly sliced. So these lengths are equal on x direction, and also the intervals from y directions are all equal. So I'm taking x and y in each rectangle in a random way, as long as this point lies inside this rectangle, it's okay to choose as a point that I can compute the height of a rectangle. So let's think about how we can find strategy first. So let's say, so question is, how can we compute this double integral? Okay, so I'm assuming that my D is also rectangular domain. Okay. So first of all, think about that I'm chopping up this x and y interval into many pieces. Divide AB and CD into n and m subdivisions. Okay. And then try to compute the volume of, is that rectangle? Is it three-dimensional? A rectangle is two-dimensional. What do you call it's the three-dimensional? I know it's cube if all the lengths of sides are equal. Square? Square is also, I think, two-dimensional. Rectangular cube, maybe. Rectangular cube. So it's not an English class, so you can say anything here. Even though it's not grammatically incorrect, it's okay. So just say anything. Compute the volume rectangular cube on this subdomain. So let's say xi to xi plus 1 and y. Sorry, I should put a small mark here. So it's represent a random point in this rectangle, and I try to mark the boundary points on the subdivisions as xi and yj. So yj. So here I have to write that what is xi and what is yj. So xi is from a to b minus a. So when I is 0, it's a. When I is n, now it becomes b. So it's evenly spaced points between a to b in the with the length b minus a over n. Okay, and yj is similar. It's the c plus j over m d minus c. Okay, and we know that I runs from 0 to n, and j runs from 0 to m. So we need n plus 1 indices and m plus 1 indices in order to have n subdivisions and m subdivisions. So that's how we define xi and yj. So I'm giving you way how you should write the mathematical sentence, because I use the term xi and yj without definition, but I just provided how this xi and yj is defined. You could write this sentence before you mention this statement. But the essence is, the point is that whenever you introduce new symbols, then you have to explain what that is explicitly. Okay, so, and then the sentence is not over. This is just a parentheses here. So compute the volume of a rectangular cube on this subdivision by taking a, you can say it's random, but it's an arbitrarily, it's more, arbitrarily is appropriate word, arbitrary point xi star and yj star inside of this domain. So this is also a technique when you write the mathematics that if you have a long description of something, then you can abbreviate that into new symbol, and you can introduce that in the before. So I'm saying that Dij is this subinterval. So I'm just putting Dij again here. And so I have to explain how we compute the small volume. So I take the arbitrary point, and I'm using that point to find out the value of function, and then that value of function becomes the height of a rectangle. And compute. So in order to find the volume of a rectangular cube, you need an area of a bottom, right? So the area of a bottom is the length of this interval times the length of this interval, and these two lengths are b minus a over n and d minus c over m, right? These two are the area of a bottom part, and then the height is f of xi star and yj star. Okay. And what do we do next? You add up all these volumes, right? Add all volumes of small or thin, we could say that thin rectangular cube as follows. So when you add something, you can only add a finite number of something, right? You learned the infinite series or infinite sum in high school or in the previous semester, but that's about the limit of finite sum. Okay? So really, you want to compute something, you can only add finite things. So we are doing a finite number of subdivisions, and we are adding these finite number of volumes by changing the indices. So when you add up these indices, you cannot start with 0 to n, because that will count n plus 1 summations. We only have n subdivisions and m subdivisions. So you have to start either from 0 to n minus 1 or 1 to n in order to find n subdivision. I'm going to use 0 to n minus 1 because that makes sense with the index here. So J runs from 0 to m minus 1, and the volume is b minus a, d minus c times fxi star yj star. Okay. Does it really area or volume between the surface of graph and the xy plane? No, it's an approximation of a volume. So in order to find real volume, how do you do that? What do you do?
We have to divide the domain to really tiny.
Right. So you can achieve a real volume by making these subdivisions really tiny, tiny subdivisions. And how you get the tiny subdivision is by increasing the number of subdivisions. So you just take n and m goes to infinity, right? So take the limit n and m both goes to infinity, okay? And check the limit. So that's what limit? So take the limit of n and m of this summation. So this summation is about function of n and m, right? Of course, there is a choice issue about xi star and yj star, but we're going to discuss that later. But if you decided that your xi star and yj star is always xi itself and yj itself, then the choice issue disappears, and it's always fixed. So it's always a matter of n and m. So we're taking that n and m goes to infinity. So it's clear what we are doing here. So we are n minus 1, j 0, n minus 1. And let's rearrange this summation here, xi star, yj star times b minus a over n and d minus c over m. Okay. So if this limit exists, you can expect that this represents the area or volume underneath the graph of function. And that's how you get the definite integral. That's how you define the integral of two-variable function. Now, there's some issue here. There's some issue that you can naturally ask. So suppose that you try to implement this method into the code or Go programming code. Is everything clear what to do in each step? What is not clear?
Well, theoretically, we can intuitively understand the arbitrary points between x sub I star and y sub j star. But when we have to make code, then we have to give an exact point to the computer.
Right.
And I think that's the ambiguous part for the computer to compute the integral.
Right. So we have to plug in specific number to xi star and yj star, right? So our intuition is this works for any way of choosing xi star or yj star, but when you really implement something, then you have to fix the way you choose your xi star and yj star. So you need a guarantee that whichever point you plug in to the formula by taking a point inside the rectangle, the result should be the same. You need a guarantee of the results is the same. So that condition doesn't come with free. You need an assumption that this limit always exists, and the limit is always the same no matter how you choose xi star and yj star inside of these subdivisions. All right? You cannot check by plugging infinitely many ways of choosing xi star and yj star into the code and see whether the limit is always the same. You need a mathematical claim that this should be always the same. So what I mean by that, as I said, I'm going to write that again because it's really important, and then I really want you to understand the true nature of integration. So the first point is that we need to choose a specific point for xi star and yj star to compute. But we also need the assumption that the limit is this limit is always the same no matter how we choose xi star and yj star. So as long as xi star and yj star lies in the subdivisions, we can take anything. But if you really want to compute something, you have to specify one. And without this assumption that no matter what xi star, yj star you choose, the limit is always the same, you cannot say that the result is the area of a rectangle, I mean the volume of a rectangle. You need that guarantee that this limit is always the same, no matter how we choose xi star and yj star. And do you have any other issue here to really compute this?
I think there's one more issue where
Mm-hmm.
still we don't, there's a possibility that we might compute the integrals of function like this,
Mm-hmm.
which is a very large value of tangent
Mm-hmm.
slope. And in that case, if we make the n and m two small values,
Mm-hmm.
I mean, if we don't divide them into very small pieces, then maybe that will cause a huge error
Right,
from the real value.
right.
So I think, yeah.
Right. So it's a really important point. So you have to you have to guarantee that the basically what Hyun-Gyu said is that we need a guarantee that this limit exists. Because if you have a function that diverges at some point, like you have a tangent asymptote plane, then if you choose some points for xi star and yj star, then function value is so large that it can cancel out the largeness of n and m, and this summation becomes very huge. And you're actually taking very large sum of many sum of the sum ends here. If you have taking like value something like 0.01, it's a comparatively small, but if you take thousands of 10,000s of 0.01, then it becomes large. And if you're taking actually infinitely sum here by taking n and m goes to infinity, then that makes this limit goes to diverge. So we need a guarantee that this limit actually exists. We need to guarantee that the limit exists, or i.e. does not diverge. Or so exist doesn't mean that always it's not diverging. So if I add one thing more on this second issue here, is that we are taking n and m goes to infinity. We're not taking n and m goes in the same speed to the infinity, right? So I can take any I can take any number of n, any m number of m. For example, I can take m as an n squared. So if I take tens of these subdivisions on x-axis, I can take hundreds of subdivisions in the y-axis, and I set this as a rule. But sometimes if I take the small subdivisions on the y-axis and comparatively less subdivisions in x-axis, it might cause a problem to find the limit. So I want to guarantee that the limit does not depend on the choice of n and m. So no matter how I choose the shape of the subdivisions, I want this limit to exists. And another issue is that I don't want the limit goes to diverge. So there are lots of issues that you have to, when you try to explain the integration as the volume underneath the graph of function, you need this criterion, or at least some assumption before you actually carry out computation. But I'm not saying that this way of writing, this way of defining the integration is wrong. It simply needs more argument than just finding the volume. Okay? So I've never seen that it's any university textbook or any actually university textbook considers that, but whenever people talk about the integration, they should talk about the integrability of a function. It's like when you talk about the derivative of a function or differential of a function, you have to first talk about the derivativity of a function, differentiableness of the function. The same thing here. So you need these two assumptions, or at least claim, to be met before you actually compute the integration. So let me define the integrability of a function, and then we move on to the integration. So I'm going to talk about the two variable function, but you can generalize to multivariable. Continuous function, for example. But actually, when you talk about the integration, you don't need a continuous function. I'm sorry. So we have function defined on this rectangular domain if there's a level of generalness of the definition of integrability. Do you want to see the most general form, or do you want to see the most concrete form? I mean the concrete, more specific form. Generally fine. Let's see how we can understand, how we can expand our ideas in the most general form. So although I choose my division into as evenly spaced subdivisions, I don't even have to make it as an evenly divided subdivision. So I'm going to define my notion of subdivisions as follows. Let x0 to be a, and x1 and xn, like the large n, to be n, and y0, ym to be d, be a subdivisions of the interval AB and CD. It's any subdivision, okay? And let's define a notion that let's choose this as follows. So we have x0 to xn. So basically, subdivision is a set of number, or you can take it as a series of numbers that from A to B. And I'm taking set here, and I'm taking let's say I want to take double bar here, because usually when you take a single bar around a set here, then it simply means the number of elements. But I'm trying to define a different concepts here. So take a double bar is the maximum of xi plus 1 minus xi, where I from 0 to n minus 1. So I'm not saying that this subdivision is evenly spaced. You could have a large subdivision in certain n index, and you have a smaller and smaller subdivision when you goes to the other limit. But I'm taking the maximum of those and taking as this symbol. It's similar for y0, ym, and I'm taking maximum among all subdivisions. Okay. So you see what I'm trying to do? So let's say, all right, so we say the function f is integrable on this domain if the limit and y0 and ym, sorry, that both goes to 0, and n and m goes to infinity. So you have a lots of limit here. What I mean by is that I want n and m goes to infinity, but also want the maximum of the largest subdivision, the length of largest subdivision in each subdivision goes to 0. So I don't want that one of subdivision stays in the same length, and all the other subdivisions goes to 0 but there could be the difference between the lengths of subdivisions, but I want generally all of subdivision goes to length 0, so basically smaller and smaller. Okay, so that's how you have a limit here, and I want xi, yj to exist. The limit is this, and then the sentence continues here, exists for any, there's two things here. So any choice of subdivisions and xi star and yj star. It's not just exist, and exist and the same. The limit this exists for any subdivision, choice of subdivision and choice of xi star and yj star, and the values are the constant. So I don't want the limit changes depending on the way I choose the subdivision and the way I choose the point inside of this each subdivisions. If the function satisfies all these criterion, then we say it's integrable. Now, when it's integrable, what does the integration mean? Integration is this value. Getting this value is the integration. Okay. And we abbreviate the notion here as the double integral sign that we introduced before. So, definition. Let f be a integrable function on a to b. Okay? Then that limit, so the limit introduce in the definition of integrability is called the integration, or more specifically, we have a two-variable function, so it's called double integral. Or specifically, double integral. And written as it's an integration over, A cross CD, which is D here. So it's written as fxy dx dy. Or there is another notation that you have probably seen somewhere. You put integral to integral, seems like an integral of single variable function, and fxy, and you have dy dx here. So basically, it's not really double integral. It's called the iterated integral, but there's a theorem that iterated integral is same as double integral in some with some condition. So I'm trying to write the notation already again here. So how you understand the change of dx dy is that this dx dy is just one thing representing that you're integrating over xy plane. But in the integrated integral, you're thinking about the integral of two integrals separately. First one is the integral over y from c to d, and the next one is the integral over x from a to b. So there are two ways of writing this, but generally it's not the same concept, but the results are the same, so I'm giving you these symbols. Okay. Now, do you have any questions about why I explained why we do this, because generally how we understand the integration is wrong. So I'm trying to give you how mathematical logic works. But the question is, so think about that, you know that you can integrate y equals to x, right? So you know how to integrate like some functions. But you never check that that's actually an integrable function, right? So the question is, how can you check the integrability of a simple function such as y equals to x? So answer is not easy. Even for really simple function, in order to check that this works for any type of division, subdivisions, any type of choice of xi star, yj star, it's not an easy issue. So you need a whole theory of analysis to make this definition in an easier form and then apply that form to check that the function is integrable or not. Yes.
Oh, well, I have a question related to the previous question that you gave us.
Mm-hmm.
Well, once I just roughly read the book. It was not a textbook. It was a book about the history of calculus and analysis. Well, I was really impressed that the Riemann showed whether the function Dirichlet function is integratable or not. Well, he did very analytically by using the epsilon and delta. Well, so I was wondering, because that kind of perspective is really good for checking whether it is integrable or not. So, is there any related theory that which can apply to the multivariable function?
There is. There are lots, actually. So it's a whole different area. So just a side talk, because we don't really need to just learn the vector calculus. We're trying to be a scholar here. So let me show you here. So the Hyunyu question is there any theory that we can check the integrability? That's the main essence of the question. And if you think about this way of defining integration, the one thing that you can easily understand is the Lebesgue integration. Usually that matches with the Riemann's integration. The Lebesgue integration is something that you can apply to a function that is defined on a domain with a certain measure, that the measure counts almost all of the area of the domain. So what I mean by measure is that suppose that you have a probability space. So you have a small chance that things cannot happen, right? But it's almost negligible. Like in a quantum mechanics, theoretically you can go through the wall, right? But it doesn't happen. Almost never happens, right? But there's a chance. So if you take the space like that, you cannot ignore the probability of that situation, but you somehow give a weight on something that could happen most likely and something that cannot happen almost all of the times. So that's the notion of measure. So measure is something that you put a weight on things that can happen or that cannot happen. So with the notion of measure, there's another way of defining an integration. So here we have a function that always defined on every point on the domain, so you don't need a measure, right? But if your function is unpredictable, or in other sense, not always defined, and your domain is also something that you cannot measure in a literally measure, that you can think of it as input and input values here, then you have another concept of integration. So that's called the Lebesgue measuring, basically. But if you think about the specific function that we know of, that Lebesgue measure is nothing but the same integration that the Riemann developed. There are other sorts of integration, and you have to define what is the integration, and then you have to define in order to make sense, that you have to define what is the integrability in the definition of integration in that certain sense. So so in order to answer questions to, is there a theory that you can check the integrability of a function? Yes, there is. So for example, in the Riemann integration, you can make this definition, the general sense of limit, into a little bit specific form that you can make n and m always equal. And you can also check that there's also subdivisions are evenly spaced subdivisions. And also you can say that this 2 points xi star and yj star should always be on a corner, an upper or lower left corner, something like that. And then you can compare the limit of certain choice of subdivisions and these points. And then if these two limits are coincides, I mean, you can, what I mean by that is if you take the limit with certain subdivisions, you get one thing. And if you take another limit with another subdivisions or another input values of xi star and yj star, you get another limit. But the series kind of tells you that if these two limits are equal, then everything in between counts everything in between. I mean, the general situation always falls into the range of these two limits, so they are almost all the limits should be equal, something like that. Okay, so it's a similar idea to our single variable function case. Then you have a Riemann sum. You can take a left sum and right sum. If your left and right sum coincide by taking the limit, then every Riemann sum is always, since always in between the left and right sum, it should be always the same. The same similar idea happens to this multivariable function case. You can check the kind of a notion similar to left sum and the right sum, and you want to see that these two limit coincide, then you can check that this limit exists. But that's how you apply to the Riemann sum case, so a Riemann integration case. So in other integrations, you need another theory. So it's a whole bunch of big theory going on here. So it's a very good question. So if you think deeply about integration itself, you start thinking about the measure of the domain, how you measure your space, how you measure your domain space, and then that goes to the very deep theory on mathematics, and it's partially related to quantum mechanics, and also so how von Neumann thought about these questions to thinking about the quantum mechanics. So if you're interested, you can read any analysis textbook, not real analysis, just think about yeah, there's a book about, I just forgot the title of that book. Just if you avoid the book, it's a book called The Real Analysis and Complex Analysis. If you just take the book about analysis, then you probably find something similar to about the Lebesgue measure or Lebesgue integration. So that's my answer. Okay, so good questions. Okay, yes.
I wonder why did you add the condition for maximum among interval?
Oh, that's a good. Right, that's a very good question. So, by taking the number of subdivision goes to infinite is not enough to check the actual volume, because, for example, I can take let's say this is my A and B and C and D. In an extreme way, so you see what I'm doing here? So I'm taking a half of each subdivisions as my first subdivision, and half of half as my second subdivision, and so on. By increasing n and m in this way, I don't actually get a small rectangle, right? So I really want to increase the number of subdivisions, but actually, if you impose these two conditions, I really don't need this condition. Third condition follows as a consequence. If I really want the maximum goes to 0, then there's no way I can increase the number of subdivisions, but also I want every subdivision goes to 0. So in order to impose that every subdivision goes to 0, I can simply impose that maximum of those goes to 0. Then everything goes to 0. So the meaning of this limit, these two limits, is that I do not want to have the fixed size subdivision in the limit. Okay? Because if I have a fixed size of the limit, then it doesn't really approximate the area or volume under the graph of function properly, right? Yes.
Professor, you can set the interval of xi and xi plus 1 is the same. You can like this. Interval is same. Why you set the max?
Why do I choose this notation instead of choosing the subdivision to be equally spaced subdivision, equal-sized subdivision? Yeah, actually, you can replace this argument with the equally sized subdivision. But I asked before I lay out the definition whether you want to see the most general form or specific form. So this is most general form. Like mathematically, it counts all type of subdivisions. You don't. If you take the specific form of like equally spaced, equally sized subdivisions, then you may ask, oh, what happens when I have subdivisions that have all different sizes? Does it really have a same limit? Then this definition cannot answer that question. But if you define this way, this comprises entire type of subdivisions, and now you need a theorem that it is enough or it is sufficient to think about the equally spaced, equally length subdivisions to compute the limit to see actually this limit exists. Then you can now move on to work on the equally length subdivisions to check the integrability or not. Okay, but that's a good question. So yeah, so just this is I chose this because this is the most general form. But what Suo said is that you can replace, with the Suo's questions, I'm saying that you can replace this argument with the equally spaced subdivisions and also taking n and m goes to infinity. And you can actually take the n and m equal more specifically. All right. So that answers what's the integration. I hope that gives you some idea about what integration is. And that makes sense to the single variable case, what I've just said. But now here's another question that's going to be another class. So we deal with the rectangular domain. Right? What if we have a round-shaped domain for a two-variable function? that my points lies inside some sphere or like a circular domain or like ellipsoid domain, elliptic domain, like not like a rectangular domain. How would you subdivide and how would you add all of this summation? How would you define the integrability? That's the next question, right? Because we don't always deal with the function that lies inside of this rectangular domain, right? Well, for example, if you want to find a volume underneath the graph in order to find actual volume of three-dimensional object, and the three-dimensional object has lying above the circular domain, circular region, then you somehow have to find out the way to calculate the definite integral over the circular domain. This doesn't tell you how to do that, because you always talk about the rectangular domain. You have subdivision for x and y axis.
Maybe, well, let's say it is in terms of x and y, then you can project the domain. Domain will be any geometrical shape. Let's say it is continuous boundary. Then we can project the domain to the x-axis, and we make a subinterval of x-axis as we just did in the previous step, and then we can limit the upper, the integral. We can maybe limit the y interval by the function that relates f and y and x. Maybe that can solve.
Can you elaborate a little bit more about the idea? I think you are in the same right track.
Well, we can choose x and y for a fixed axis, and then we make a subinterval just as we did in the previous step. And then the problem is, even the x is constant, the y still changes. The interval of y that we have to integrate is changes. So we can map the x to y, and then if there is a function that maps x to y, let's say that is function g, then we can take integrals to like the most lower g to the most higher g, then larger g. Then we can integrate smoothly.
Okay, so I understand now. So basically, Hyungyu said that if you have a non-rectangular domain, you can you can set a map from x to the minimum of y and maximum of y, and you try to integrate over that x values of a function, and then try to integrate over x. So basically, that's iterated integral. So you're integrating for y and then the x. So that's correct. That's correct way of defining the volume underneath the function over this round thing or round domain. That's about the integrated integral. And there's another way of defining double integral, like we defined in here, even for non-rectangular domain. And the issue is that when we explain those two concepts, there are quite different approaches. One is, I'm not going to spoil you here. So one is the very simple idea that how mathematics usually do when they expand or generalize the specific concepts. And another is that what Hyungyu actually said, you integrate on this y domain, and then you integrate over x domain. And then question is why these two strategy gives the same answer to the integration. That's also a good, interesting question, because usually you don't get the same answer if the function is very weird. So that happens with certain condition, that what Hyungyu said for the iterated integral is same as the how mathematics define the double integral with certain condition. So it will be interesting if we see the example that these two are not equal. Okay. So I think this is end of our class. I try to do the project that we have not done yet. So I gave the project for giving a code for writing the code for partial derivative. I tried to do this in today's class, but maybe we'll do it next time. So, all right. So the next time we're going to discuss that double integral and iterated integral on a general shape domain. And as I said in the beginning of the class, I have graded your midterm, but I'm not going to give you the mark unless you're taking your midterm in person. So you have to actually see what I commented on your midterm answers. So either you come to the class or you come to the office to see the midterm papers. All right, thank you very much, and see you on Friday.